So let's get the ball rolling. We are looking at dynamic cost productivity. We've already looked at dynamic productivity. And the dynamic productivity has to do with input-output combinations. Input-output combinations. But there's a problem with that. Okay. Let's try to get a problem associated with that. The classical productivity measurement, we call it classical just to distinguish it from the cost. It is Malmquist productivity change. The person who spotted the idea was Christensen and DeWitt. Caves, Christensen, and DeWitt, 1982. But it was Fair, Groskopf, Lindgren, and Roos who operationalized it using linear programming. And they pioneered that whole setup there. Now, these guys, Fair, Groskopf, Lindgren, and Roos, they are not the only one. Fair, Groskopf, these professors in Oregon, Fair, Groskopf, Norris, and Zahn, they are the ones that brought the three-part decomposition, which was criticized by Ray and Desley in 97. And then Fair, Groskopf, and others in 1997. So all of these people extended the usual Malmquist productivity index as we know it. So Wheelock and Wilson, we remember we looked at his own, they did a four-part decomposition. So this whole thing about Malmquist, classical Malmquist, it was done for cases where input and output levels are available, but input prices are not available, or if they were available at all, they were ignored. They were not incorporated. The prices of the inputs were not captured. And that was a big issue. You're going to see that pretty soon. Why? Because to estimate the cost Malmquist productivity, that index requires that you incorporate input prices. So it uses the input costs rather than the input distance. So it uses the input cost distance function. And it assumes, which is practical though, that producers are cost minimizers. In other words, even if they don't control the price, because remember the input price are exogenously determined by the forces of demand and supply, by the invisible hand of Adam Smith. And so even if they don't control the price, they are able to do something to the input so that when these inputs are multiplied by the price, cost is minimized. This point is an important point. So you need to have the output and input price, okay, being exogenously determined but are available. If they are available, even if they are exogenously determined, you are able to estimate the cost Malmquist index because you're able to minimize the cost. And that point I just said is important. So you are, before you can minimize costs, you've got to minimize the input. Why? Because the input, when minimized, the cost untouched will go along with it. And that is why the cost Malmquist is able to help to estimate allocative efficiency. Because allocative efficiency, as we got to know the last time, is that after you have determined your technical efficiency. That is, having been able to reduce your input, which is input technical efficiency, you now go ahead to now mix those inputs in an effective allocative way. So you're able to change the input mix that produces the output, which then brings about allocative efficiency and hence allocative efficiency change. If you look at the book by Coeli et al., 1998, and later on they had a 2005, amendment to the 1998, you will get that sense of allocative efficiency and its change. So the Cost Malmquist was introduced by Maniadakis and Tanasolis in 2004, published in European Journal of Operational Research. In there, they are able to explain allocative efficiency. And what is that? It tells you the degree to which an already technically efficient firm can further. So remember, it's already technically efficient. That is input technically efficient. Can further cut the overall cost of securing that given output. So the output is more or less given. You are not going to raise the output. You are rather reducing the input. But you are reducing the input, which will make it technically efficient, and then select an optimal input mix, given the exogenously fixed prices. The paper by Tanasolis et al., 2015, also published in European Journal of Operational Research, explains further. They use the Cost Malmquist and extended it to group. So you kind of have group Cost Malmquist. So I'm just giving you a bit of theory about a Cost Malmquist. 2004, Maniadakis and Tanasolis extended the classical Malmquist, also called input-output Malmquist, to incorporate Cost Malmquist productivity change. And with that productivity change, you can decompose it like the normal one, the normal Malmquist, the classical Malmquist. You can decompose it into efficiency change and technological change. Here too, you can decompose it into cost efficiency change and cost technological change. So it's just a matter of bringing the cost under it. What Maniadakis and Tanasolis did is that they did their work under the assumption of constant returns to scale. Okay. So note that constant returns to scale, they assume that all firms are operating at the same optimal scale size. However, we know that financial constraints, certain, oligopolistic and, monopolistic competitions and other things can make firms not operate, leverages can make firms, capital structure, minimum requirement, regulations, all of this can make firms not operate at the same optimal scale size. They decompose the cost efficiency change into tech efficiency change and allocative efficiency change. Okay. So that was a two-part decomposition that you saw at the top. Now this is a four-part decomposition where the cost efficiency change itself is split into the classical version, allocative efficiency change, and then allocative efficiency change. And then the cost technical change was also decomposed into the technological and then the price effect. Look at it from here. This picture will give you a better understanding of all of it. In one of the papers I wrote in the Geneva papers, we just gave this picturesque understanding. So Cost Malmquist is split into cost efficiency change, which is also called overall efficiency change, and then cost technical change. And here's the beauty part. The cost efficiency change is split into normal efficiency change and then allocative efficiency change. Whereas the cost technological change is split into technological change and price effect. But when you pick the efficiency change and the technological change, that will give you the standard classical Malmquist. Okay. So you will get back to that. And that's a very beautiful thing because we shall use this chart to do further extensions. Okay. Now, anytime you are discussing cost Malmquist, and I had to do some of them, last month. Anytime you are discussing cost Malmquist, you want to let the reader know some of the extensions of cost Malmquist, and then the applications of cost Malmquist, the extensions and the applications. What are some of the extensions? Well, some of the applications have been applied in the health sector, the insurance sector, banking, electricity, real estate, forest, and product industries and educational or schools. So when you look at these papers, Tohidi et al., they did an extension of the cost Malmquist to the global Malmquist. Wall here actually looked at cost Malmquist related to some negative data. One, et al. 2015 considered one cost Malmquist, meta Malmquist, I would say, or meta frontier cost Malmquist. Canasolis extended it to group cost Malmquist. Tohidi and Tohidina looked at profit Malmquist. Ohiniasari applied the cost Malmquist to the insurance sector and Amasebi. So all of these are extensions of the cost Malmquist. So don't discuss the cost Malmquist when you're discussing it in your thesis or in your paper without letting the reader know that they are, further work. And please, these are not exhaustive. So go and look for some of the recent applications. I would say from 2015 up to date, look for recent and find the most recent application and include that whenever you are writing about a cost Malmquist. All right. So let's get some bit of definitions here because definitions are very important to make you get a picture. Let us assume that we have a time period because this is productivity, so it requires time. And you have a data you collected at time t, which is time 1, 2, 3, 4, all the way up to time capital T. You can have a balanced data or an unbalanced data. I'll talk about this later because all of the existing ones, they talk about balance. It appears the majority of studies are not talking about unbalanced data. And there's a way to handle that. The number of DMUs, if they are balanced, and the number of DMUs in 1 year are 30, what it means is that the DMUs will be 30 in every other year. That is a balanced data. So the DMUs number 1 to n, where n is the total number of DMUs. And if the total number of DMUs are 30, then it means n is 30. These DMUs consume inputs. These inputs are members of real positive autons, and they use those consumed inputs to produce some outputs. So we can define the production technology. Watch this. I am defining the production technology. We are defining it based on the Shepard 1953 approach. The production technology can be defined in an output direction or in an input direction or in an input-output direction. Okay, so take note of that. So we'll talk about the production technology. You can define it in those different ways. So you can have X1 and then X2 definition of the production technology. You can have that. Okay. That is one way you can look at the production technology. Another way is you can have Y1 and then Y2 definition. And you can have X and then Y definition of the production technology. The one we are looking at is this one, the X1 and the X2. That is why we are talking about input distance function. So we are defining the production technology in an input distance function. So I'm about to write the input distance function. What is the input distance function? What is it? How do you define that? Okay. Now, let me show you the mathematical. And again, if you don't understand any slightest thing about the mathematical jargon, let me know. This is a distance function. The I here is indicating input orientation. The XTYT is indicating an input-output correspondence, or a DMU. Okay. And this distance function is equal to the supremo with a subscript of theta. Now, you might be wondering, what is that supremo with that subscript of theta? Now, you may have heard about infimum and supremum. If you haven't, okay, these words are quite infimum and then supremum. These are some mathematical derivations that we tend to talk about. What is that? These are abbreviations. And so the supremum, okay, or the supremum is the SUP that I have here. There's that. That's the SUP that I have here. Now, what is the difference between infimum and supremum? This, when we talk about the supremum of a subset, okay, let's say of a subset of a partially ordered something. Okay. If I give you that, the supremum of that subset is the least element in that set, okay, that is greater or equal to the element of it. So if that element exists at all, that is it. In other words, we tend to say that it is the least upper bound. Watch the word. Is the least upper bound. Why? I want you to take note of this. The distance function that you are seeing here, in an input orientation, this distance function is greater or equal to 1. The distance function is given by greater or equal to 1, which means there are other numbers like 1.5, like 2.5, and then going on like 3 and all of that. So when we say the least upper bound of this, the least upper bound. Now, this distance function is reciprocal is the technical efficiency scores. And what is the technical efficiency score? The technical efficiency score you are seeing is this theta. So the theta is the technical efficiency score, which is below 1. So if it is below 1, then the upper bound of that number is 1. And below that 1 are numbers below the upper bound. Now, the distance function is a reciprocal. So when you look at this, okay, there are upper bounds here. There are upper bounds for the distance function, but the least of this upper bound is 1. So you are using the supremum to capture the least of the upper bound. Okay, and that is why you can see that we have defined this to be greater than 0. Okay, theta is greater than 0, which means that it is positive. But of course, this theta, which is positive, okay, is a reciprocal of this distance function. And if it is a reciprocal of the distance function, okay, and the distance function is greater or equal to 1, then the theta is less than or equal to 1. Then the supremum of the distance function is that whole thing that you are seeing inside the information. Okay. So how do you get, what does the x over the theta mean? Now the theta here is efficiency score. So x divided by that theta, obviously, is a way you are reducing the input. So this x here is an input, and you are reducing the input as this theta increases. Okay. By the time theta increases to 1, this input has been reduced to its minimum. What about this? This is a input requirement set or the isocost. Okay, this LT is an isocost which with a given output that you have. All right. So this is how you explain some of these things. I'm giving you this thing because sometimes when you are presenting your work in a thesis panel and somebody doesn't understand, because not everybody might understand, you want to be able to understand these mathematics so well that people will be able to appreciate that you have knowledge of what you're saying. Okay. So you're just not writing, but you also have an understanding of whatever you're writing. Okay, so the I is the input orientation. The LT is a set of input vectors, okay, that generates a set of output vectors. Now, here's the thing. Given the input prices, and remember the input prices is also a vector, that input price, that positive input price, then we can define the cost technology function. Now, what we defined here was the input distance function. How will you define the cost technology function? This is it. The cost technology function is defined as C into bracket Y W all to the power T, indicating that we are dealing with the current time period T. So how do you get that cost? That cost is obtained by minimizing the set. And what is the set? Look at the set carefully. Okay. This set is, this first part is the observed cost. So what you see here is observed cost WX. W1, okay, let me just say WX is the price of the input multiplying the input. So that is observed cost, okay, which is such that that input here, that input is inside the input requirement set. And of course, the price of the input are also positive. They are not zero, but they are positive. So this is what we are minimizing. So you have an observed cost, and then you try to minimize that observed cost to the barest minimum. When you're able to do that, you are becoming cost efficient. Okay. So this observed cost is supposed to be multiple. So if it is Wij and then Xij, then you can sum all of them. So this vector is a matrix of this, is a summation of all of the inputs multiplying the prices of the input, all of the prices of the input multiplying the input. And therefore, whatever you get here, the C here means the minimum cost. So the C to the power T, Y to the power T plus W to the power T is the minimum cost of producing the given output, given the exogenously fixed price, okay, and of course, given the technology. So this is a minimum cost basically, okay? And the minimum cost, if we combine the input vectors, this is interesting. If you combine the input vectors, each input vector corresponds to a scalar, which is this. Okay. If each input vector, which corresponds to a scalar, lie on the isocost line, remember, we're going to see the isocost line. The isocost line is the boundary of the cost technology. Then we can say that we can define the isocost line or the cost boundary as what you have down here. It is simply the minimum cost, but it's a line. So we put a bar on top of it. So basically, it's a minimum cost, but it's a line. Because when the minimum cost is like a point. And because you're talking about all the points put together, making up a line. The minimum cost is a point like this. This another point, this another point, this another point, this another point. When you put those points together, you can now have what? A line. And that line becomes the isocost line. That is what is defined. And that isocost line happens because we have the observed cost being identical to the minimum cost. Your capacity to explain these terms, like I said, is very important. So you should be able to learn how to explain them. Okay, enough of this. Once you have your minimum cost, Okay. And you have your observed cost. We'll look at an example. Once you have this minimum cost, remember the minimum cost always has the capital C outside the bracket. The observed cost is just W and X. That's the observed cost. Then if you divide the minimum cost by the observed cost, now watch it. You will notice that the minimum cost pass into brackets Y and W. But the observed cost has Y and X. The observed cost has Y and X because, sorry, W and X. Because W is observed, you see it. X is observed, you see it. Okay. Y is also observed, W is observed. But here, the minimum cost here is for those that are given. So this, because the Y is given, because you're not going to reduce Y, you're not going to increase Y. And because the W is exogenously determined by the invisible hand of Adam Smith, they will define the minimum cost. So the minimum cost is like a benchmark. It's like a standard everybody wants to reach. But everybody will have their own observed cost. And their goal is to minimize that. Therefore, the cost efficiency, which will capture all these three elements because it's handling both minimum and observed cost, is just the ratio of the minimum to the observed cost. So to get the minimum cost, you need to have the observed cost. That's what I mean. Okay. To get the minimum cost, okay, you need the observed cost. To get the observed cost, you need the input and you need the input prices. But you can't control this price match. And so your goal is to what? Minimize the input, which will mean that you are minimizing the observed cost. And when you get to the minimum of that observed cost, it becomes simply the minimum cost. So that is a principle that we're going to take to estimate cost efficiency. All right. Now, once you've estimated a cost efficiency, which is also called overall efficiency, you can decompose that into technical. We know this already. I'm just going faster. And then you can decompose it into technical efficiency and allocative. And the technical can be split into pure technical and scale. And then the allocative will happen as it is. Therefore, we can use the principle of change of subject to find allocative efficiency, because allocative efficiency is simply going to be the cost divided by the technical. All right. But we can use distance function for this. And when you're using distance function, remember that the distance function is just a reciprocal of the efficiency scores. So here you have a distance function there, and that distance function is the reciprocal of the efficiency scores. So if this is the technical efficiency score, input technical, then its reciprocal is a distance function. And so we can formulate a linear programming problem that will minimize the input. Even though I'm going to look at cost efficiency, I'm going to give you a model that first minimizes the input, because remember what I told you, first you have an observed cost, but this W is more or less given. So you got to minimize the X, the input. So we need a linear program that will minimize the input first. This is it. So look at the linear program, the first one here. You see, I have written the efficiency because the reciprocal here is more or less technical efficiency. The subscript C means I'm dealing with constant retention scale. The fact that you have superscript T, okay, T, means that we are dealing with time period T, or the current time period. How do you find that score? How do we find that distance function to the power -1? How do we find the reciprocal of that distance function? Well, you find that by minimizing the theta. Remember, what you see here is the actual theta star, more or less. So what you see here is the theta star, the actual value. And that is given by minimizing the theta subject to the constraint that the weighted sum of the input of all the DMUs, including the one you are minimizing, is less or equal to the input of the DMU that you are reducing. And because it's an input orientation, we attach the data to the input. And then you generate your output constraint. The output constraint says the weighted sum of the output of all DMUs, including that very DMU that you are minimizing, its input, its output, that should be greater than the output of the DMU that you're looking at. That is a targeted or the evaluated DM. The constraint that you see here is the convexity constraint. Remember, Tanasolis and Maniatakis, they considered only constant returns to scale. So to them, this constraint was not there. But I've brought it here for a reason, because you will notice later that you can do this thing also in variable returns to scale. The non-negativity constraint is already there. Because we are assuming VRS here, theta is free. It's free to become CRS, it's free to become IRS, the firm is free to become DRS. And then, of course, your DMUs are here. This is for own period. So this is known as own period efficiency, own period. Look at the next one. The next one is also own period, but it is for a firm in the second year. The same thing. Watch the difference. Watch the difference, because in your thesis and formulation, you got to bring all of this. The difference is that if you look at the technology will have T plus 1 throughout. And then if you look at the evaluated DMU, it will also have T plus 1 for both the input and the output. Remember, it is the input and the output that are raised to the power T plus 1. It's not a lambda. It's the input and output that are raised to the power T plus 1. And the fact that all of these are T plus 1, T plus 1, T plus 1 means that you are doing own period efficiency. So this is also own period efficiency or own period distance function. So this own period efficiency score is saying that assess the efficiency of firm in year T plus 1 relative to frontier T plus 1. So the outer term is the frontier, the inside the bracket is the DMU. Okay. The third one is a cross period. Now, what is a cross period? The cross period here says that you are estimating the efficiency of a firm in year 2, but relative to the frontier 1. So that is what is known as cross period. Sometimes it's called mixed period efficiency. Cross or mixed period efficiency. I'm taking my time with this mathematics so that you can grasp it. Now, watch something here. Once what is in the bracket is the one you are estimating, but it's just relative to the frontier in the previous year. Once that is the case, it means that the frontier, because this is a frontier, and remember, the frontier is the technology here. It means that the X and then the Y will have T, because the frontier is T. And then because the DMU is in year T plus 1, on the right-hand side, which represents the targeted DMU, that will be the T plus 1. So this is cross-period efficiency. And the last one is another cross-period efficiency, this time of a firm in year T, but relative to frontier T plus 1. Watch it. T plus 1 on the left, T plus 1 on the left, T plus 1 on the left. Okay. T on the right, T on the right, T on the right. Okay. That is how you formulate this model. And of course, the software will run all of this for you, but you got to understand what is happening and know what each evaluation means. So that is for the input you are reducing. Remember, I told you that you have to reduce the input first, okay, given the exogenously fixed price. Then that will help you to get the cost. So we've done the input. So cost efficiency requires, it's not just cost minimization, but it requires input minimization first. And once you have been able to estimate your input, you should be able to remind yourself to let us know the input-oriented Malmquist Index. What is the input-oriented Malmquist Index? Well, that's what you have here, but it's different from the one year. It's not different, but it's a reciprocal of the efficiency score. So what you are seeing here are the distance functions. The distance function D, and its reciprocal is the efficiency scores. So what you see theta here is technical efficiency. Technical efficiency. Now my question to you is this: tell me, what has changed between this Malmquist Index, input-oriented Malmquist Index, and this input-oriented Malmquist Index? Who can tell me what has changed and why has that change happened? Miriam, what has changed and why has that change happened? What has changed and why has that change happened? Yes, Michael.
The change I see is that the numerators of the input Malmquist has been defined by the distance functions. Is now the denominators of the input Malmquist, which is defined by the thetas. And this change, we see this change because the distance function is a reciprocal of the thetas.
Good. So which one is correct?
They are both correct.
Okay. Emily, do you get it?
Doc, yes.
Now, what will be the value? What will be the value for this one here? We expect the value to be what? Is it greater than 1 or less than or equal to 1? The value here, is it greater than 1 or less than or equal to 1?
The value for the first one is greater than or equal to 1. And for the second is less than or equal to 1.
Say that again.
I said the value for the first one is greater than or equal to 1. And the second equation that we see is less than or equal to 1.
So what does it mean here when the value is greater than or equal to 1?
In the
so is that
first
what
equation,
you chose?
Yes, for the first one.
Michael, what I'm showing you, is that what you chose?
Yes.
Okay, so what does it mean?
It means that the particular DMU that we are assessing is inefficient.
Suppose the value here is 1.25. What are you saying?
I'm saying that the firm or the DMU that we are assessing is inefficient by 25%.
But when you interpret it like that, that is not the best of interpretation.
Okay.
Doc, can I come in?
Yes, Emily, come.
Okay, so since you are dealing with productivity, it means that they regressed their productivity, as in their efficiency reduced. But since you are dealing with distance, it's better to find the reciprocal so that we can better find the percentage that it's reduced.
Okay, so find the reciprocal.
And
then interpret that and let's see.
Okay, so the reciprocal is going to be 1 over 1.25. And then the answer, please, someone should help me. I'm not having a calculator with me.
Those of you who are not answering my other questions, answer her. Miriam and Co.
It's 0.8.
Okay, so that it means the efficiency is 0.8, meaning they have regressed productivity by 20%.
Very good. That is excellent. So productivity has reduced by 20%. That's what it means. So if you look at the 1.2 alone, you are going to say that productivity has increased by 20%, but you have to take the reciprocal. This is an input orientation. It's an input orientation. And this is important. Unless you are using the efficiency scores. But Michael, even if you are using efficiency scores, your results is still going to be the same. If you are using efficiency scores, you are still going to get 1.25. Who can tell me why? For the second one. Michael, you thought that the results will be different, right? Is that what you thought?
Yes.
Francis, are you there?
Like what we did earlier, 1.2.
Michael, continue. What did you say?
I'm saying that, yes, the results will be different because one is the reciprocal of the other.
Yeah, what I'm saying is that if you look at this formula here, and you look at that formula there,
Okay.
You are saying that the results going to be different.
Yes.
Doc,
And
no.
I'm saying that the results are not going to be different. Emily, were you saying something?
Yeah, I was saying it was not going to be different because in the formula itself, they've already done the reciprocal.
Yeah.
Exactly. That's why I want you guys to pay attention for me. The reciprocal itself has been taken care of in the formula. And because remember, each theta that you have is less than or equal to 1. Each distance function is greater than or equal to 1. And so, first of all, whatever value you have, the reciprocal itself is taken. And that is why you swapped the formula. So if you look at this formula, the numerator here is rather the denominator here. And so you are still going to get that value. And whatever value that you get, you have to still take the reciprocal. Input orientation, take the reciprocal. Output orientation, you don't take any reciprocal. Whether you are using distance function or you are using efficiency scores. Once you are dealing with output orientation, whatever value score you have. So output orientation, when you get a value of 1.3, what it simply means is that productivity has increased by 30%. You don't take any reciprocal, you leave it and interpret it as it is. Michael, exactly.
Yes, Doc.
Any question again on this? Now let's move on. Now, when you look at this whole information, we can decompose the efficiency into two, the Malmquist into two parts. And this is all in the paper by Fair, Groskopf, Lengren, and Roos, or Fair, Groskopf, Norris, and Zhang. The first part is the efficiency change, which is a catching up to the frontier. The second part is the technological change, which is a frontier shift. We know this already, okay? But there are other decompositions and there are other disagreements regarding constant and variable returns. Go through this by yourself because they are all there in the other videos and in the other lectures. I told you that you cannot go to cost productivity unless you understand input output productivity or the classical productivity. That's why I've gone through all of this. Now, how do you formulate the cost Malmquist productivity in DEA? Let's have a balanced or an unbalanced panel. Okay. Balanced or an unbalanced, but for now, let's write it as if we are balanced. In fact, when we write the notation, nothing even shows that it's balanced or unbalanced. But we have a panel of firms. In each time period, they are consuming some inputs available at some prices, and they are using these to produce some output. A particular DMU, for that DMU, its actual cost or observed cost of securing that input is given by this value. And this cost, which is all in year T plus 1, and this other cost, okay, where you are measuring the unit of the firm in year T plus 1, but relative to frontier T. All of these are respectively the weighted sum of the input, or the input price times the input. So keep that in mind. On the basis of that, Maniadakis defined the cost Malmquist as dual, two different, cost distance functions. And I want you to understand that point very well. Okay, so we have two different cost distance functions. What's the first one? The first one is the cost distance function, the cost productivity relative to time t, and the other one is cost productivity relative to time t plus 1. Now, pay attention to the definitions you're going to see here, because this is where some people get it wrong. What is this? Who can tell me what this is? What is WTXT plus 1? Francis, are you there?
Yes, Doc.
YM?
Yes, Doc.
Is it that I asked you a difficult question? That's why you were not responding.
No, I responded.
Okay. What is the 1/2 circle?
It is the cost.
If you are to take away
rate.
the reciprocals, if you have to take away the subscript, the superscript, ignore the superscript for now. What is that?
So the WX is the cost.
Emily, what is that?
Okay, Doc, is the price times input.
What is that?
That's observed cost.
It's not cost. It's observed cost. It's not cost. It's observed cost, or it's actual cost. We are very particular with words. So keep that in mind. Now let's go to this one. What is this? Michael?
It's the minimum cost.
What?
Minimum cost.
Minimum cost, correct. So watch it carefully. What is WX divided by C into bracket WY? What is that? What is this whole thing then? Can't tell me this. What is that? What is that? If you have been following the discussion throughout, should you be able to tell me what that is? Michael?
No, is it cost efficiency?
Yes, but look at it carefully. What is that? It's not really the cost efficiency, but what?
Allocative
Look, I think
efficiency.
it's the distance.
It's not allocative efficiency. Francis, you were saying something.
Is the distance cost efficiency.
That's it. It's a cost distance function. Please write it down. Is the cost distance function. Why do you say that, Francis?
Because it's the reciprocal of the cost efficiency.
Thank you. What do you mean by is a reciprocal of the cost efficiency? Explain it using the words.
So the cost efficiency is the minimum cost over the observed cost. But if you look at this, is the reciprocal. So now you have the observed cost over the minimum cost. So it should be the distance function.
Thank you. I love you. That's it. Kizito, do you follow?
Yes, Doc.
So the reason why I'm paying attention to you is that sometimes you see some of these things in papers and you gloss over them, you ignore them. And I want you to look at them carefully. We can't gloss over it. This is a learning environment. So cost efficiency itself, cost efficiency is given by the minimum cost over the observed. And the observed is always the WQ, WX. And the minimum is the one that starts with the C. But what you are seeing here is rather the observed over the minimum. So it's a reciprocal of the cost efficiency. So it means you are dealing with distance function, and this is cost distance function. Michael, I'm sure you get it now.
Yes, Doc, I get it.
Okay, now that we've gotten what is always, and so take note that always in this very example, because we are using distance function, always the C is the denominator. So if you go and check all the formulae, every time you see these two formulae, one divided by the other, the denominator is always a C, is the minimum cost, because we are dealing with distance function. Okay, now that you've understood that, let's go to talk about what it really means. Remember that productivity requires 4 different efficiency scores. So here we require 4 different cost distance functions. And if we require 4 different cost distance functions, then what it means is that we got to know the distance function that is at play here. What distance function is at play here? Now, let's take the bottom one first, the bottom one here first. What will make this bottom one to be own period cost distance function? Who can tell me? What makes this own period cost distance function? What makes it own period cost distance function in year T? Emily.
Okay, Doc, we are looking at it in their own time periods. So for the first one, inputs in period 1, multiplying the price of period 1.
Mm-hmm.
Okay, so Doc, for own periods, it's when the DMUs in question are being observed by their own frontiers, or is being
measured relative to their own.
Yeah, measured relative to their own time periods, yes. Their own frontiers.
Okay. So what defines the frontiers here? For example, when you look at the information I've circled here in blue, what is defining the frontier? What will tell you that this is a frontier? We have several things. Which one?
The frontier will be the C superscript T.
Thank you. Excellent. Beautiful. So guys, note that the one that is defining the frontier, whether the frontier is in the time T or time T plus 1, is the superscript of the C. And by the way, whatever the superscript of the C is is the same superscript the W will have. Take note. I'm giving you some clues. The same superscript that the C will have will always be the same superscript that the W will have. And what will define the DMU that you are analyzing? So please note, we said the C and the W will define the frontier, and then the X and the Y will define what? The DMU. And that also means that whatever superscript X is having, it will be the same superscript Y will be having. Miriam, do you understand what I'm trying to say?
Yes, Doc.
Explain.
So what I understand is that whatever period the X would be in is the same period the Y would also be in.
Give me an example.
Okay, so an example is if the DMU is in period X.
Give me an example here. An example here.
Okay, an example is we have XT, and then we also have the denominator for. Okay, so we have the YT and the XT for the denominator with the underlined blue. Hello?
Are you sure you are done? Are you done? Or you are waiting for us to know whether we are listening to you?
Yes, I'm waiting to know that if everyone.
Everybody is paying attention and listening to you. Nobody has stopped listening. The floor is yours. That's all we've done.
Okay, so we have the denominator, which has been circled blue. The X is period. The X is in period T, and the Y2 is in period T. So it shows that they are all in the same period.
Do another example.
Okay, so another example.
Okay, so Christabel, so the first thing I want to go over quickly so that everybody will be clear of what is happening is that I asked the earlier question that which one is the observed cost and which one is the unobserved cost. I asked the question, which one is the observed cost and which one is the minimum cost? So let me circle here. This was the one I circled. So Christabel, which one is the observed and which one is the minimum cost? Oh, you weren't here when we discussed that, right? Emily, remind us.
Hello.
Go ahead.
Okay. Doc, should I go ahead?
Yeah.
Okay, the observed cost is W subscript T, X subscript T. Sorry, superscript T. And then the minimum cost is the C, that's the second one.
Okay.
The C superscript T into brackets W and Y. Okay.
So that ratio stands for what?
Doc, it stands for the distance, cost distance function.
Good. So that ratio is a cost distance function. And we indicated that normally when you are estimating efficiencies, whether it's cost or technical, you normally determine which one is the DMU and which one is the frontier. Here, we indicated that which ones do you use to determine the DMU?
The C superscript T is the DMU, or sorry, the C superscript T defines the frontier, and the X and Y defines the DMU.
You forget about the superscript for now. Which ones determine the frontier? Which one determines the DMU?
So the C determines the frontier, and the X and
I didn't
Y.
get that. Your network went off.
Oh. The C.
Okay.
The C determines the is the frontier, and the X and Y. X.
Okay, so I got to know consistently the X and Y. Okay, determines the DMU. But then the other one, you choose only C. And it's not only C, it's a C and W. Did you have that in mind, Emily?
Okay.
That wasn't the one answering.
Now I'm asking that, did you have that in mind when
Yes, Doc.
she was missing that one?
Yes, because you mentioned it, that the C and W are always the same, and then the X and Y are also always the same.
Yes. So, Christabel, the C and then the W, they always carry the same superscript. You got to write it down.
Okay.
I think that sometimes when you guys write things down, you better get it than waiting to go and read again. Because the thing is that when you write it down, then you have something to go and read.
Okay.
So these two will always carry the same superscript, okay? Whereas the X and Y will also carry the same superscript. And therefore, if I am measuring the frontier, so when you look at the one down here, this means that we are looking at the efficiency of firm in year T. Okay, this is how you look at it. Efficiency of firm in year T relative to frontier T. That's what it means. And when I was mentioning firm in year T, I was looking at this. When I was mentioning frontier in year T, I was looking at this. So who can interpret this top one here for me? Efficiency of what relative to what? Cost distance function of what relative to what? Who can interpret that numerator part? Emily.
Okay, Doc, so the one circled in red is saying that we want the cost distance function of a firm in period T plus 1 relative to the frontier T.
That's it. Now, who can interpret this for me? The one on the bottom right here. Kizito, can you interpret that?
Doc, please let Emily say what she said again. Please.
Okay, Emily, repeat.
Okay, so we are looking for the
can't
cost
see your
distance
screen.
function.
Kizito, just hold on.
Hello.
Someone is answering.
Okay, we are looking for the cost distance function of a firm in period T plus 1 relative to the frontier T in period T.
Okay. Thank you.
Okay, so who can interpret the one on the bottom right? The one on the bottom right. Anybody can do it. I'm talking about this cycled one. Yeah, go ahead. Emily.
Okay, Doc, so for the bottom right, is saying we are looking for the input cost distance function of a firm in year T relative to the frontier in period T plus 1.
Good. When she was saying a firm in year T, she had this in mind. Relative to the frontier in year T plus 1, she had this in mind. So that is how you define it. So here, there are two own period efficiencies. These are own period, and then there are two cross period efficiency. That's it. That is what make up the cost Malmquist. You got to fully get it and then fully interpret. But watch something. Okay, there's something you guys need to note. And what you need to note is that we can convert this one here, the top one here, and call it cost efficiency. Okay. You can call it cost efficiency. So if you look at it, I am calling it cost efficiency. So what does the first one here mean? So you can see that this one, we have put all of them together. So this first one is saying that because we have the X and the Y having the T plus 1, I told you they move together. So we are looking at the efficiency of a firm in year T plus 1 relative to frontier T. Okay, that's what you see here. And then this one here, the bottom here, is talking about the efficiency of a firm in year T relative to frontier T plus 1. So that is how you consider this cost function. You have to know that just the value here, which is the cost distance function, is reciprocal is the efficiency cost. And that is what you see here. Okay. Its reciprocal is what you are seeing here. Okay. So know how we examine all of it. But we are going to be using the distance functions too. Okay. What is this Cost Malmquist saying? All it's saying is that, okay, the distances, okay, so the ratios, each ratio, we mean observed cost over the minimum cost. Okay. Each ratio is looking at the inflation factors that we are considering, because remember, we are examining distances, and these distances, you know, are rising or are falling. Caves define these things, use the term inflation and deflation factors. But you need to know this. This is the main cost, Malmquist. You need to know this. Understand this very thing that we have done here today. Understand it fully, because once you get this, when we go to the decompositions, you'll not get lost. This is the thing. This is the ultimate. This is the cost distance function. And I could not just write it cost efficiency like this, because you need to have some feel about the, and this is important, about the observed cost and then the minimum cost. You need to have a feel of that. You need to have the observed cost separate from the minimum cost. And you will later know why. Because the observed cost is different from the minimum cost, and the minimum cost for every firm is also different in reality. The observed cost of every firm is different. Maybe some are the same, but generally it's different. And the minimum cost of every firm, for every firm, is also different. Some are the same, but it's also different. So it's important you understand this equation. That's why I'm delaying a bit of time there. Because once you crack this, there's no way you can understand the decomposition, because the decomposition makes things complex. The decomposition are complex, but they all are using these four terms. Okay, let's get some of the definition. What is this WX? Okay, forget about the superscript for now. What is a WX? It is a sum of the individual costs, the production cost. It's not quantities. If it was quantities, it would have been just W, but it's the individual cost. Now, what is this ratio? If you look at this ratio, we've said it multiple times, is observed cost over the minimum cost. But that is not cost efficiency. That is cost distance function. Because cost efficiency is minimum cost over the observed cost. So what is cost efficiency? What is a cost distance function? Because the cost distance function is greater than 1, okay, we say that it's measuring the extent to which the total cost of production, okay, in period T can be reduced. So we are reducing the aggregate cost of production whilst, or let's say, given the output and the input prices. Let's cut down the cost given the output and the input prices. The extent to which we can cut, if we are able to cut down the cost by more, and there is no more opportunity to cut down the cost further, we are 100% efficient. But if there's an opportunity to cut it further, then we are cost inefficient. That's what this ratio is looking at. But please note that the cost, even though we are calling it the cost efficiency, or let me put it this way, the cost distance function here. The cost distance function, as you know by now, is observed cost over the minimum cost. Okay. Watch the word. It is a value over a value, but it's a distance. I want you to keep in mind that it's a distance. It's a distance. And so we can use distance function to measure it, even though we can also use an actual value of observed cost or actual cost divided by an actual value of minimum cost. It's still a distance. And we can use distance to look at it. And DEA can help us to use distances to look at it. Yes, Christabel.
Doug, please, why is it a distance?
The cost distance function value is a distance because you are looking at how far this observed cost, let me just circle it. You're looking at how far this observed cost is from this minimum cost. So if I tell you that I want you to look at how far A is from B, then we are looking at a distance, isn't it?
Yeah.
That is why it's a distance. So we can use distance functions or linear programming to estimate these distances.
Okay.
And so we are going to use DEA to measure each of these distance functions. We're going to use DEA to do that. How? Watch this. You remember that when we're estimating the input distance function, we had 4 different input distance functions. And then we slotted each one of them into the productivity measure. And but it's the same thing we are going to do with the cost. It's the same thing here. So watch the cost distance function for all of this. Okay, let's look at the first one. This, we are going to look at the own period cost distance function. How do you look at it? Well, it simply says that, and this is going to give you a minimum cost, take note, for a particular DMU. So I need this cost. I need this cost. I need this minimum cost. What makes it minimum? What makes it minimum is this C. That is what makes it minimum. I need it. How do I get this minimum cost? Okay, you can get this minimum cost by minimizing this observed cost. What is that? It's also a cost, Because remember, I can't get a minimum unless I have an observed, a maximum. So I'm going to minimize this observed cost. Okay, this observed cost, okay, I need to minimize it for a particular DMU. How do I know it's for a particular DMU? It's because of this knot. This knot means that it's for a targeted DMU. How do I know it's a cost? It's a cost because we have the W and we have the X. That's what gives me an idea that it's a cost. Why do I have the summation? And why is the summation to M? Because the number of inputs, remember, the inputs are I, and it is from 1 to M. So the M is indicating the number of the inputs. So if the inputs are 7, then I have to now multiply each input price by the input itself and then sum them. Then I'll get the total observed cost. I'm going to minimize that. So if we are to do it, actually, it's something like W1, X1 for the first input, plus W2, X2 for the second input, plus W3, X3 for the third input, plus W4, X4 for the fourth input, and no. That is what makes up the summation. Remember, we know a value for this. We also know a value for that. We also know a value for this. We also know a value for that. We also know a value for this. We also know a value. So we know the value. So it's just multiplying and summing. And then you can get a particular cost, say 300. A 300 is too much, it's observed. But now we need to reduce it. How is the linear programming going to help us to reduce it? Okay, watch. This how is this. It's subject to this constraint. The constraint is the same as the previous one. The weighted sum of the input of all the DMUs should be less than the input of the firm under consideration. So don't forget that. We have inputs. 2, the weighted sum of the output of all the DMUs should be greater than the output of the DMU under consideration. Now watch. It is greater than the output of the DMU being evaluated. So let's say the output are Y1, Y2, then Y3. Okay? The output of the DMU, specific targeted DMU you are considering, that is what is on the right-hand side. Guys, you are going to formulate this cost distance function. That's what I'm showing you. But watch the input. If you look at the input here, the input is not that of the specific DMU that you are evaluating. Okay, is the input, a particular input. Because at this stage, by this stage, the input has already been minimized. I want to repeat that. The input has already been minimized. Remember the previous one, the previous formulation, we have already minimized the input. Now that you've minimized the input, now you add that input to the cost, or you add that inputs to the W. So now you now have a cost, and then you are minimizing the cost. Yeah, Mimi.
Yes, Doc. So what if the input is greater than 1?
But I've not said input is less than 1. Have I said input is less than 1?
It's less than or equal to 1. It's
where is that? Where is that written?
okay, it's less than or equal to inputs.
So the inputs you are seeing here, this is the sum of all the inputs. So whatever number, let's say that there are 14, DMUs. These 14 DMUs, they all have this input 1, input 2, the sum of all these inputs, and then separately, and then the sum of all these should be less than or equal to the input of the DMU. Okay, it should be less than or equal to the number of inputs of the DMU. So let's say that one of these DMUs, its inputs are 4. Okay, its inputs are 4. Then I do a weighted sum of all these inputs. Okay, less than or equal to that input that you are actually considering, which has been minimized already. Okay, that input that you're considering. Okay, I don't want to use this because this input will not have been minimized. This input may not have, it is observed input, which may not have been minimized, but if it has been minimized, that's great. Then that's the input that you're dealing with. But then if you look at the output, this output is the observed, the actual output of the DMU under consideration. It's the output of the DMU under consideration. Okay, now watch something. When you look at the left-hand side, is the technology. We've said this multiple times. And it is the X and this one that shows the. So please note that these values, the X to the power T here and the Y to the power T, they are because of this CT. The CT, the T is the technology, is a frontier technology, and that is what is defining the left-hand side of the equation here. Yes, Emily.
Okay, Doc, my question is it because we are dealing with the distance function that the theta no longer comes in?
Yes.
For the constraint.
No, we are not dealing with that because we are not minimizing the input here. If we were minimizing the input, okay, the distance function would have come. But we are not minimizing the input. You know, I kept saying that the input have already been what?
Minimized.
That is why on the far right here, you see that we have taken that blue one, we have taken that input. And what we are doing is that we are minimizing the cost.
Okay.
Let me repeat that again. The prices themselves are already fixed. So we are minimizing the cost, but then the cost that we are minimizing is because of the minimized input. The cost, which is the WX that we are minimizing, that cost actually is an observed cost. And that observed cost, so when you have that observed cost 300, inside that 300 is a minimized input. And that minimized input will cause this observed cost to a minimum level. So coming back to your point, this is not an equation to minimize the input, it's an equation to minimize the cost. That's why we don't have the theta.
Okay, Doc.
But you cannot do this one unless you've done the previous one. In principle, you cannot minimize your input. And when we go to the R software, you will understand it, you'll enjoy it. You cannot minimize your cost unless you have minimized the input, because the input minimized is what minimizes the cost.
Okay.
I think you understand that.
Yes.
Now that you've gotten this, the next thing now to do, of course, as always, is to have your non-negativity, the convexity constraint. So this is a convexity constraint. It's normal. There's no to the power T attached to it. Then you have your non-negativity constraint. And then here you are being told that the input is positive. So this is how you formulate an own period. Watch it. What makes it own period? It is this subscript T, superscript T, superscript T, superscript T. So if I were to tell you that right now, I want you to formulate the same thing for T plus 1 own period, could you do it?
Yes, Doc.
Yes, Doc.
Okay, who can tell me how to go about it without mentioning what to do, but how? What would you change? First of all, what would you change?
Like you change the frontier, the time period of the frontier to T+1.
Which one will you change?
The C and then the W.
So you mean this C and this W?
Yes, though.
Which other one?
And the W at the last, at the right hand side.
This W.
Yes.
And then so the point is that you will change all the T to T+1. All T to T+1. So it's not only T here, because I said own period for the second year. Okay. So
Okay.
you change this one to T+1, you change this one to T+1, you change this one to T+1. Yeah. Let me show you how the rest will look like. If it was a cross period, I didn't say own period. A cross period of which firms in year what relative to which frontier, which year's frontier. That's the next thing. If we're looking at a firm in year T relative to the cost frontier in year T+1. A firm in year T relative to the cost frontier in T+1. Only C here will change. Oh, sorry. A firm in year T, yes, relative to cost frontier, only C here will change to T+1. And then the technology will also change to T+1. But everything else will remain as T.
Doc, what about the W?
Yes, thank you. The W will change to T+1. Good, you got it. If the frontier is changing, anytime C is changing, the W will change with it. And those ones are the ones that I have gotten here. So look at this. So when you look at this screen, it summarizes everything. So if you look at the first one here, that is the own period. Okay, that's the own period. And when you look at this, they are all T. When you look at this bottom one too, it's also own period. Why? Because everything is T+1, okay, T+1. And then this one too is T+1. And this one is T+1, T+1. But the cross period are different. The one I did some few minutes ago is rather this. Okay. So that's the one Emily said, this one must also change to T+1. The technology will change to T+1. Okay. The W inside and the C will all change to T+1. Remember, the DMU is in year T. But if you have check consistent, in all cases, we don't touch the X. Watch it. In all cases, we don't touch the X. We don't touch it. We don't give the superscript to the X. You can tell me why. You said it before. You can tell me why. Emily.
Doc, because the X has already been minimized.
That's it. When you are formulating your thesis, you need all these 4 equations together with the 4 equations for the input distance function. You need all this. As for the convexity constraints, I've given them a color of red because we will be doing the constant returns. But if you are doing variable returns, then you need to bring this convexity constraint. Don't just look at it. Okay, you should be able to tell the reader that this is the non-negativity constraint. That is a convexity constraint. This is, non-negativity for the input, okay, any of the inputs, okay? And this is the time period. You need to be able to identify everything so that the person will know that you know what you are saying. Everything. So this must be nicely given. Then we are done. Once you've estimated this, what's the next? The next thing is that, and everything that we have estimated is explained here. So the cross period was calculated using model that this is own period, but you can see, sorry, this is cross period because we have brought t plus 1 here. And we're saying that after changing the t to t plus 1, okay, whilst the constraints and the prices remain the same using this period. So everything that we said. So once you estimate each of these 4 different cost distance functions, you can put it into the productivity formula. That strange looking, beautiful formula. And then you can now get your score. Whatever score you have, don't forget the interpretation. Less than 1, watch it. Because we are using distance function, less than 1, okay. And I've done something here, okay, for a reason, because when we finish our score, we will take the reciprocal of the score. So I am calling it now less than 1 is progress. No, we don't take a reciprocal. There's less than 1, generally less than 1, as we know, is progress, and greater than 1 is regress, because this is an input orientation. We've said it before. And then, of course, this one is constant productivity, which means productivity stagnated. But here's the point I wanted to make. Depending on which software you are using, if you're using MaxDEA will give you the results straight away, so that greater than 1 is rather progress. When you're using benchmarking, because benchmarking is using efficiency scores, okay, you will get the score being greater than 1 progress. Distance function, if you use distance function, which you can also use in benchmarking, it will give you the score less than 1 to be progress. The only way you can understand this is when we work an example. But in general, understand these 2 main differences. The Cost Malmquist deals with distances by which input cost can be deflated. Deflated from where it is to reach the cost boundary. That is different from the standard Malmquist or the classical Malmquist. The classical Malmquist, okay, or the Malmquist itself, distances, okay, are where input quantities are deflated, not input cost, but input quantities are deflated to reach the boundary of the production. But this one, they were reaching the boundary of the cost. So you should know the difference. When you're interpreting, these differences must be there. Okay. So in summary, this is the Cost Malmquist chart, and this is the decomposition and how you connect the 2. This is all under what? Under constant returns to scale. So you see that we don't see anything called pure technical allocative or pure allocative scale. There's nothing of scale here because we are not dealing with VRS. Yes, Mimi.
Yes, Doc. So does it mean that because it's Cost Malmquist, that is why when it is greater than 1, productivity is greater than 1, it's inefficient? Because previously,
you cannot use the word inefficient in productivity. So change the word inefficient. Okay, start your question.
When it is. Okay. So I said, is it because it's Cost Malmquist? That is why when productivity is greater than 1, it's regress. But when it is less than 1, it's progress. Because previously,
it's not only because it's Cost Malmquist. It's also because we are dealing with input Malmquist. Both cost
Okay.
Malmquist and input Malmquist. And please, I want you to understand something. I'm saying that value, you can take the reciprocal and then make the interpretation for progress to be greater than 1. You can take the reciprocal of your answer. So if you calculate the cost Malmquist to be 0.5, we know that it is, because it's less than 1, that is progress. You know that. But when somebody looks at the number, it doesn't make sense. So you would take the reciprocal. So I would now say cost Malmquist reciprocal is 1 over 0.5, which will give me 2, which now makes progressive sense. That is proper progress. So now you can interpret it and say that the firm has progressed between year 1 and year 2. The firm has progressed by 100%. Productivity has increased by 100%. Do you get it now?
Yes, Doc.
Because my mind, your mind is on the fact that it's 200 means that it's increased by 100%. So it's just by taking the, but as it is, when you calculate it as it is, you will get a value of less than 1, which means progress. When we get to the software, you will see me use that reciprocal thing a lot. But it's good to get to the final answer. And going back to your earlier question, Emily, that also applies to all the decompositions, the components.
Okay, Doc.
So when we come, so each one of the components, you're going to explain it the same way. Watch, before you explain it, like I said, my advice is that make it greater than what? Take the reciprocal so that it becomes nicely interpretable. That's it. That's a theory. That's the theory of this whole Malmquist, cost Malmquist thing.